Welcome back to the Deep Dive. We're here to tackle complex tech, find the strategic core, and really equip you to be the go-to person in your next big meeting. Today, we were doing a really big deep dive into microservices architecture, MSA.
Yeah, it's absolutely fundamental for basically any modern platform you can think of. But, well, the complexity is pretty notorious. Our mission today isn't just defining it. We want to explore the strategic trade-offs, the hidden costs versus the long-term gains you need for real scalability and resilience in your organization.
Okay, let's try and unpack this. There's a great analogy that really helps. Think about building software. You've got the traditional way, monolithic architecture. Picture like an ancient statue carved from one single piece of rock. It's massive, tightly coupled.
Yeah.
Every single part depends on every other part.
And then the contract is microservices.
Yeah.
Here, you deliberately break the application down into, well, we often call them Lego bricks. Each brick is self-contained, it operates on its own, and it's built around a specific business function, a business capability.
That immediately brings up the strategic question for you listening. Moving to microservices, it's not just a tech swap. The sources really emphasize this is a strategic imperative. You're consciously choosing more technical complexity right from day one. So we need to understand why. Why do companies take on that initial, pain?
Well, the motivation usually starts when that monolith, that single block, really becomes a scaling bottleneck. I mean, for a small team, it's great initially, development simple, deployment straightforward. But as that code base just grows and grows, every tiny change, every deployment means you're touching and testing that whole massive thing. Deployments get slow, risk goes way up.
And this is where those Lego bricks really start to shine. The first big advantage is enhanced scalability. So let's say you run a flash sale. Only your inventory service gets slammed with demand, right? With MSA, you just scale that one service. You don't have to spin up more resources for the entire huge, expensive application just for that one function. That's incredibly cost effective.
Exactly. And that independence, it leads straight to better resilience too, through what we call fault isolation. So if one service fails, maybe the recommendation engine has a bug, the problem stays there, it's contained, users can still log in, they can browse, they can check out, the rest of the app keeps running. You avoid that catastrophic system-wide crash that would just take down a monolith instantly.
Yeah, that resilience is crucial. But let's shift a bit. What about teams feeling locked into a specific technology? I really like this idea of technology flexibility. Because the services are independent, you can create what's called a polyglot environment.
Polyglot. It just means teams can pick the absolute best tool for each job. Maybe Java makes sense for this service, but Python is better over here, or go for something else. You're not stuck with one stack for everything.
And then maybe the most strategic benefit, the one that really impacts the business long-term, is organizational agility. Microservices let you scale your development teams, not just the application.
Right. You break the app into these autonomous pieces, and you can have small, focused, cross-functional teams work on their own services. They own them, they deploy them, all in parallel. That speeds up feature delivery dramatically.
Okay, so the long game is scalability, resilience, speed, huge benefits. But we have to talk about the cost. If you're a CIO listening, when do these promises actually pay off? Like, at what point is this initial complexity, this upfront pain, really worth it?
That pain is definitely real. The fundamental trade-off is that increased complexity. You've gone from managing one big rock to juggling potentially hundreds of these little Lego bricks. That means multiple code bases, different ways to deploy them, different ways they talk to each other. It adds significant operational overhead.
Think about managing deployment pipelines, monitoring everything, just basic upkeep.
And because these bricks have to talk to each other, they're usually communicating over a network, right? So those inter-service calls, they add network latency. You can run into performance issues right away if you haven't designed it carefully. Yeah. And security gets trickier too. You mentioned resilience, but the flip side is that a distributed system has a much larger attack surface, more points of entry to worry about.
So what's the takeaway here? It sounds like the complexity and the operational load, they're basically the price of admission.
That's it exactly. It's the non-negotiable cost you pay up front for that long-term flexibility and resilience you need to keep growing at scale. You're trading today's simplicity for tomorrow's viability.
Okay, so if you're paying that complexity tax, you absolutely have to make sure you're getting real independence out of it.
Right. Because the worst case scenario, and it's really common for teams starting out, is creating what's called a distributed monolith.
Ah, the distributed monolith sounds bad.
It's the worst. You get all the complexity of microservices, but none of the benefits because everything's still tangled together. You've made it complex and tightly coupled.
So how do we avoid that? We need some design rules.
We do. It starts with the single responsibility principle, or SRP. Basically, each microservice should do one primary thing, aligned with a specific business capability.
Okay, one job per service.
Pretty much, and that naturally leads to needing loose coupling and high cohesion. Services need to be independent. They own their own code, their own data, and you minimize how much they rely on others.
But that brings up the million-dollar question. How do you decide where one service ends and another begins? Where are the boundaries?
That's the toughest part strategically. And the framework for tackling this is domain-driven design, or DDD. DDD forces you to think about your application in terms of the business, the core business capabilities, not just technical layers like the UI or the database layer.
And within DDD, there's this key concept, the bounded context. Can you explain that?
Sure. A bounded context defines a specific area, a boundary, where a particular business term or entity has a very specific meaning. Let's use customer as an example. In a sales context, maybe the customer needs attributes like age, their purchase history, maybe lead score.
Okay, sales cares about that stuff.
Right. But now think about the support context. For them, the same customer means something different. They need, say, contact address, maybe recent support tickets, detailed purchase history for returns. They don't care about the lead score. By defining these separate contexts, sales and support become truly distinct microservices, even though they both deal with the customer. They own their own view of that entity.
And if you don't use DDD, if you just start chopping up your monolith based on, say, database tables?
That's where you risk creating that tangled mess. The sources actually have a great terrifying name for this: the Death Star architecture.
The Death Star architecture, wow.
Yeah, where everything is slightly connected to everything else, making changes incredibly risky and failures just ripple outwards. One small hit, and the whole thing can explode.
Okay, definitely want to avoid building the Death Star. So, assuming we've used DDD, we've got these nice independent services, they still need to communicate and coordinate for complex tasks, right?
Absolutely. And that's where specific design patterns become essential.
Right, like managing who gets in the front door. You need a kind of bouncer.
Exactly. That's the API gateway. It acts as that single front door for all requests coming from outside, from clients. And it's not just directing traffic. It handles crucial stuff like security authentication, authorization, and then routes the request to the correct internal service.
And I've heard of a variation, the backend for front end, or BFF.
Yeah, BFF is a refinement of the gateway idea. Instead of one giant gateway for everyone, you might create a specific tailored gateway for each type of client. So maybe one BFF optimized for your mobile app, another for your web app, another for internal tools. It helps optimize performance for each specific front end.
Makes sense. Now, what about when things go wrong? Failure happens in distributed systems.
It's inevitable. And that's why the circuit breaker pattern is so important. Think of it like an electrical circuit breaker in your house. If a downstream service starts failing repeatedly, throwing errors, timing out the circuit breaker trips or opens, it stops sending requests to that broken service for a while.
Ah, so it stops the problem from spreading.
Exactly. It prevents a temporary glitch in one service from causing a cascading failure that takes down everything else relying on it.
Yep.
It gives the failing service time to recover.
Okay, last big pattern here, transactions. This sounds really hard when each service has its own database. How do you keep data consistent across services?
It is hard. You can't just use a traditional database transaction that spans multiple services. So we use the Saga pattern. A Saga is essentially a sequence of local transactions across different services. Each step is a transaction within a single service. If any step in the sequence fails, the Saga pattern defines compensating actions to undo the work done by the previous successful steps.
So it's like a controlled rollback across services.
Kind of. Think about booking a trip. Book flight, step 1. Book hotel, step 2. Charge credit card, step 3. If charging the card fails, the Saga would trigger compensating actions to cancel the hotel and flight bookings. It maintains consistency over the whole business process, even though it spans multiple services.
Okay, we've really established how complex this distributed world is, and the sources are super clear. You just can't get the benefits of microservices without serious, robust automation. Which brings us to, like, the foundational tools you absolutely need.
Absolutely. Automation is non-negotiable, and it really starts with containerization. This is all about packaging your application code, along with all its libraries and dependencies, into these neat, portable, self-contained units called containers. Docker basically became the standard way to build and run these containers.
Right, so Docker packages it up neatly, but then you might have hundreds, maybe thousands of these containers running across lots of machines. How do you manage all that? Manually sounds impossible.
It is impossible at scale. That's where orchestration comes in. And the dominant tool here, the industry standard, is Kubernetes, often called K8s.
Kubernetes. Everyone talks about Kubernetes.
They do, because it automates the deployment, scaling, networking, and overall management of all those containers. It works on a declarative model. You basically tell Kubernetes the state you want, like, I need 10 replicas of my payment service running reliably. And Kubernetes handles all the underlying work to make that happen and keep it that way, even if servers fail.
Wow, okay. So Kubernetes is like the master controller for the whole distributed system. That sounds like a big thing to learn and set up.
It is a significant investment, yes, but it shifts the burden. You stop managing individual machines and start managing the desired state of your application. It's crucial for operating microservices effectively.
Okay, let's talk traffic flow. We mentioned the API gateway for requests coming in from the outside. That's sometimes called north-south traffic, right?
Correct. External client to internal system.
But what about the communication between the services themselves, inside the system, that east-west traffic?
Right. For that internal service-to-service communication, we often rely on a service mesh. Think of it as a dedicated infrastructure layer woven throughout your microservices. It typically works by deploying a small, lightweight proxy, often called a sidecar, right next to every single instance of your services.
A sidecar proxy next to every service. What does that do?
It intercepts all the network communication going into and out of the service. And this allows the mesh to provide powerful features consistently across all services, like sophisticated traffic routing, failure handling, and crucially, security.
Ah, security. How does the service mesh help there?
It's fundamental for implementing a zero-trust security model within your cluster. The principle is never trust, always verify, even for internal communication. The service mesh can automatically enforce things like mutual TLS, MTLS, between services. This means every service cryptographically verifies the identity of the service it's talking to, and all that internal traffic is encrypted. It secures the gaps between your services.
Okay, that's a big security boost. Switching gears back to data for a second. We said each service owns its private data. How do they share information or react to changes in other services' data then?
That often leads us to event-driven architecture, or EDA.
Event-driven. So things happen and services react.
Pretty much. Instead of services directly calling each other to ask for data, a service will publish an event when something significant happens within its domain, like order created or inventory level updated. These events go onto a central message bus or event stream.
Like a notification system.
Exactly. Other services that care about that event can subscribe to the bus and get notified. When they receive the event, they can update their own local data store accordingly. This leads to what's called eventual consistency. The data across the system isn't guaranteed to be perfectly consistent at every single microsecond, but it converges and becomes consistent very quickly as events propagate. It maintains that loose coupling.
Okay, eventual consistency. That's another key concept. Finally, observability. If a user clicks a button and that request travels through, say, 10 different microservices, how on earth do you figure out where a problem is or where the bottleneck is?
Yeah, tracing a single request across that distributed landscape is a huge challenge. Simple logging isn't enough. You need distributed tracing.
Distributed tracing, how does that work?
It involves propagating some context, like a unique trace ID, with the request as it jumps from service to service. Each service adds its own timing information or spans to this trace. You need tools to collect all this data. OpenTelemetry is becoming a standard for generating this telemetry data. And then you need visualization tools like Jaeger or Zipkin to stitch it all together.
So you can actually see the entire journey of that one request.
Yeah. Exactly. It gives you that end-to-end application-centric view. You can see exactly how long each step took, which service called which other service, and pinpoint exactly where failures or slowdowns are occurring. It's essential for debugging and performance tuning in MSA. So we've covered a lot of the tech, the patterns, the tools, but honestly, the sources are really emphatic about this. The single biggest hurdle to succeeding with microservices isn't the technology. It's the required organizational and cultural shift.
It's not optional, they say. It's a prerequisite.
Absolutely. You can't just adopt the tech without changing how your teams work.
And this shift sounds significant. It means ditching those traditional large siloed teams, right? Like the database team, the UI team, the backend team.
Gone. You need to move towards small cross-functional teams that are organized around specific business capabilities or domains. Crucially, each team needs end-to-end ownership of its microservices, From writing the code to building, testing, deploying it, and importantly, monitoring and supporting it in production. You build it, you run it.
That sounds like a massive change for management, too. It requires letting go of control, doesn't it?
Yeah.
Decentralized governance.
It really does. Managers aren't coordinating one big project anymore. They're enabling and supporting the autonomy of these smaller teams. And this autonomy only works if you have a really mature DevOps culture already in place. You need that automation for continuous delivery, shared responsibility, good monitoring. Otherwise, giving teams that much autonomy can just lead to chaos. Every team essentially has to become an operations team to some extent.
Right. That end-to-end ownership is where the speed comes from, but it demands different skills, a totally different mindset from the organization. So to convince people this potentially painful cultural change is worth it, let's look at some real-world examples, the giants who really proved this model works.
Netflix is probably the most famous case study. They famously migrated from a monolith to microservices years ago, specifically to handle their enormous global scale and the unpredictable nature of streaming demand. Their ability to deploy constantly and stay resilient, they even developed key tools like the historic circuit breaker pattern we mentioned, really demonstrated the high availability benefits. And they were pioneers in running that polyglot environment and using different tech where it made sense.
And Uber is another classic example, right?
Yeah, very similar story. As they grew globally, their initial monolithic code base just couldn't keep up. It slowed down development, made deployments risky, so they broke out core functions, things like managing customers, drivers, payments, mapping into separate services. This dramatically accelerated their ability to launch in new cities and roll out new features, really proving the organizational agility promise of MSA. So, okay, the architecture clearly works for these giants, but we keep coming back to the operational overhead. It's significant. And that's why the current industry trend, where things seem to be heading, is all about finding ways to abstract away that complexity, to make MSA easier to manage.
How are we doing that? I keep hearing about serverless computing. That sounds almost too good to be true for managing microservices. Like, no servers to manage.
Well, serverless is a bit of a misnomer. There are still servers somewhere. But the point is you don't manage them. Platforms like AWS Lambda, Azure Functions, Google Cloud Functions, they let you deploy code, typically small functions, without worrying about the underlying VMs, containers, or operating systems. The cloud provider handles all that infrastructure management.
Okay, so it pushes the operational burden onto the cloud provider. How does that change the equation for someone deciding on MSA?
It changes it quite a bit. Your team's focus shifts away from managing infrastructure and towards writing business logic, managing costs, and optimizing the functions themselves. And it pairs really well with event-driven architecture, which we discussed. Instead of having a whole service running 24/7 just waiting for a message, you can have a cheap, ephemeral serverless function that only spins up when a specific event triggers it. That can lead to big cost savings and much simpler operations for certain kinds of workloads.
Interesting. And what's the other big trend helping manage complexity?
The other major one is AI-driven automation, often called AIOps. Basically, using artificial intelligence and machine learning to make sense of the absolutely massive amounts of data generated by a microservices environment. All the logs, traces, metrics from potentially hundreds or thousands of services.
So AI helps sort through the noise.
It goes beyond sorting. AIOps aims to move monitoring from being reactive, waiting for an alarm, to being proactive. For instance, AI might analyze historical data and predict that your streaming service will see a usage spike next Friday night, then automatically scale the necessary services before the spike hits. Or it could look at anomalies across dozens of seemingly unrelated services and correlate them to pinpoint the root cause of a complex issue much faster than a human could. It directly tackles that observability and operational complexity problem.
So ultimately, we keep circling back to that core idea. You accept the upfront complexity, the operational learning curve.
Because it's the price you pay for getting that future agility, scalability, and resilience. That's still the fundamental strategic trade-off at the heart of microservices.
Right. That's the strategic heart of it.
Yeah.
So wrapping this up, what are the key takeaways for you, our listener? First, it seems like culture eats strategy for breakfast here. Really do an honest organizational self-assessment. Is your culture ready for DevOps, for end-to-end ownership? Get that right first.
Absolutely. Second, don't just jump into coding. Start with the strategy. Use domain-driven design, DDD, to figure out your service boundaries based on actual business capabilities before you write a line of code.
Yeah.
Get those boundaries wrong, and you're in trouble.
And third, you have to invest in the right tools. There's no avoiding it. You'll need robust automation, so plan for Kubernetes, for Docker, likely for a service mesh eventually. They're foundational.
And maybe here's the final thought to leave you with. talked a lot about how the biggest barrier to adopting microservices is that high initial complexity and operational overhead. But if these future trends we discussed, like serverless abstracting, infrastructure, and AI ops automating monitoring and even decomposition, if they continue to mature and eventually do automate away much of that initial technical heavy lifting, does that high upfront complexity cease to be the main strategic barrier? And if the tech hurdles become significantly lower, what new organizational, cultural, or maybe even ethical challenges might emerge then as the primary focus for engineering leaders? Something to think about.